So we have two talks in the session, and the first talk will be by Xiao-Gang Wen. The title is Emmanent and Emergent Symmetry-Modular Categories for the low energy spectrum.
Yeah, thank you. Yeah, I really like to thank Nati, Mike, and Ashwin for organizing such a wonderful meeting. And I see so many old friends, so such a wonderful gathering. And so what I'm going to talk about is this emanent and emergent symmetry from the low energy spectrum. And so the idea is that we have some kind of a spin system which have this kind of a spectrum. If you only look at the low energy part, and then we have this low energy effective field theory. And the low energy effective field theory may have this emanent or emergent symmetry. The emanent symmetry actually is a lattice exact symmetry. But however, in the low energy effective field theory, it may take a very different form. Yeah, this concept is introduced by Meng Chen and Nati Seberg, and which is very useful for us. So that's allow us to describe our results more precisely. And also our work follow analysis of Meng and Nati's paper. Emergent symmetry is basically approximate symmetry, which it became more accurate at the low energy, but may be broken at a higher energy. So I think recently the year we realized that emanent and emergent symmetry can go beyond the groups. And the classical theory, classical symmetry basically is defined by invariance under some transformation, and the transformation can be composed. So this became automatic. When we say symmetry, we mean group. Yeah, but this connection now is broken. So actually the low energy emanent or emergent symmetry in quantum system is really defined by the algebra of so-called low energy allowed local operators. There are some local operators which are allowed, which define allowed operations. And this allowed operation define symmetry in quantum system. So this algebra, we call this a local operator subalgebra. So certainly from this operator algebra point of view, the equivalent algebra would describe equivalent symmetry. Because the symmetry have a many different definition of equivalence. So this particular equivalence, we call this a hollow equivalence. And it turns out that this hollow equivalence class of symmetry actually is not classified by group. It's by something else. So we believe that this symmetry is really one-to-one classified by this Brady tensor higher category. And yeah, this sounds like a scary name, the Brady tensor category, but actually in some sense it's like an onion model with a braiding and the fusion. You can view this category as an onion model. And certainly this n category, this n means a spatial dimension. So symmetry at a different spatial dimension would describe by different n category. Yeah, this level of n is a spatial dimension. Also, not every category describe symmetry. There are only some requirements, like they have trivial center or trivial width class, you know. And trivial center means this onion model can be realized by lattice. And the trivial width class means this lattice realization allow gap the boundary. So that's a physical way to say this. So this kind of Brady tensor category have many physical names. It can be called a categorical symmetry, or symmetry topological field theory, or symmetry topological order, or topological holographic. So, but all this representing this mathematical object is kind of Brady fusion higher category. Okay. So so one way to understand this categorical theory of the symmetry is via this holographic view of anomaly. You know that the symmetry anomaly is described by this Weissenmiller-Witten term in one higher dimension. That's kind of some early work in the 1980s. Then we also have this invertible gravitational anomaly. The perturbative one are described by this gravitational Chern-Simons term in one higher dimension. And also there's a global one, which associates diffeomorphism, which is not connected to identity. And then after the introduction of topological quantum field theory or this topological order, and this study of a boundary of those topological theory, then it's then we have this kind of more general understanding of this holographic view of anomaly, which can be summarized in such a statement. That is invertible and non-invertible gravitational anomaly classified by this topological field theory or topological order in one higher dimension. And because the topological field theory or topological order are described by a braided tensor higher category, so therefore the gravitational anomaly are also described by braided tensor higher category. So that's kind of a connection. Then this non-invertible gravitational anomaly is kind of a special in the sense it's a partition function is a vector valued. And the usual invertible gravitational anomaly have a partition function whose phase factor is ambiguous. And here the ambiguity is even described by a unitary matrix for non-invertible gravitational anomaly. And in the real Zhang's work, they point out that anomaly in the symmetry can be detected by this modular non-invariance of this vector valued partition function. And also we find that this even anomaly-free symmetry are related to this vector valued partition function. So those observations connect anomaly with symmetry. In some sense, it's kind of natural. You know, gravitational anomaly is a way to have a constraint on low energy dynamics. The symmetry also provides a constraint to low energy dynamics. So in this sense, both are kind of similar. So then that's led to this opinion or conjecture that symmetry is actually non-invertible gravitational anomaly. And then because gravitational anomaly are described by topological field theory or topological in one higher dimension, so that provide this holographic view of symmetry, and this in turn gave us this categorical theory for the symmetry. Certainly there's some detail, like the symmetry is really up to this hollow equivalence. You know, there's some details, but generally the symmetry and the category are very closely connected. Okay, so therefore, so the symmetry really is in general really beyond the group. So we need some category to describe symmetry. So that's it. And this is I want to say this is a very general way to look at the symmetry. If using categorical theory to describe symmetry, this automatically include the anomalous symmetry and the higher form symmetry or non-invertible symmetry or their mixtures. So since all kind of symmetry can be described in this categorical way, this kind of unified description. Okay, so those are something very abstract connection. So here we try to find some simple applications. And again, the simple application is, again, we want to compute emergent symmetry. But now the difference became, before when we compute emergent symmetry or emanent symmetry, we want to compute a group, or maybe compute its anomaly. But now we feel that to compute emanent or emergent symmetry, we should compute a braided tensor category. So we try to find some kind of simple, doable physical example or some physical computation, whose result produce a category. So how to have a calculation which produce a category? So that is basically the issue here. But remember, category is basically the onion model. It have a few onions with a braiding and with a fusion. You know, so computing a category just computing the onions basically. Okay, So we just pick a very simple, very familiar example, which is basically the Hasselmann model. But the Hasselmann model have a SO3 continuous symmetry, and the category for the continuous symmetry is not very well developed. So that's one of a big open question. So we break continuous symmetry down to this discrete symmetry. So we consider this XYZ model. And so this GX, GY, GZ coupling are very close, but not exactly the same. So therefore, the spectrum is still very similar to Hasselmann model spectrum. We define the low energy sector. And then we ask, in the low energy sector, what is emergent or emanent symmetry? Basically, we want to compute what is this modular tensor category. Or in other words, we want to compute what are the anyons. Okay, so this can be done using just to exact normalization. And so this is basically this is a SO3 Hasselmann chain. So we can study this higher symmetry point for the Hasselmann model on the ring of 20 lattice site. Okay, and on this kind of lattice, and we see that from momentum point of view, there's two sectors. One low energy sector is near momentum 0, another low energy sector near momentum pi. So that means the translation symmetry on the lattice, which is ZL. But in the continuum, you only see two sectors. So this ZL reduced to Z2. And then we also have so this crystal momentum just described this Z2 representation for the translation. And then certainly we also have a X spin rotation and a Z spin rotation by pi. So we have two other Z2 quantum number. So total we have 8 Z2 quantum number. So therefore there's 8 representations, or maybe we see actually there's 8 anyons. So those are states carried by these different Z2 charges. Okay, and so basically this spectrum, this representation tell us, yeah, there's at least 8 anyons. Okay, and all these states are one-dimensional representation. So this anyon may have a quantum dimension 1. Okay, and also interesting that some of the representation have a crystal momentum 0 or pi. So that means those anyons have a topological spin, which is 0. But there's a few exceptions here. It have a non-zero crystal momentum. But however, this crystal momentum happen to be this 2 pi over L with the coefficient of 1. So if you measure crystal momentum in terms of 2 pi over L, that tell us topological spin, which is 1. The topological spin 1 and 0 is equivalent from anyon model. They're all bosons. Yes.
What happens to the rest of the translation? You have the Z2, but then there's a continuum.
Yeah.
In the field theory, there's just continuous translation.
That's exactly. So that's where the eminent part comes from. You know, for on the lattice, all those momentum are well defined, are quantum numbers. But however, here we do have this spectrum, and we say there's a low energy sector and a high energy sector. If you only look at the low energy sector in field theory, and then these small momentum are just a field theory momentum. But however, this crystal momentum pi became a field theory internal symmetry. Yeah. So then we only keep this internal symmetry. This internal symmetry is eminent symmetry, but it really from lattice, so they are always exact. Yeah.
Is there a gap between what you call low energy excitation and high energy excitation?
Yeah, this is a good question. Yeah, this is just a, I don't know. I think there should be more precise definition, but I try to say that if you take L go to infinite limit, the low energy effective field theory describing this part of the spectrum. what I try to say, you may say, let's pick 1 million low energy spectrum. When L is big enough, this 1 million spectrum is a part of low energy factor field theory. Certainly, this you can take 1 billion, but as long as L is big enough, this is a low energy factor field theory. So it's you need to take certain limits. Actually, this is crucial because that's why we want to consider this Jx, Jy, Jz about the same. If they are very different, the spectrum is very different. So low energy sector, low energy field theory is very different. So it's different discussion. So actually, I don't have a very precise way to answer your question, but I almost like to say that I almost want to use this emanent symmetry to define what is the low energy effective field theory. Because later we want to study the physics where the low energy sector interact strongly, but the high energy part remain unchanged. I don't know what I mean by that really, but I can only say, well, what I mean is that somehow I can turn on very strong interaction in low energy effective field theory without breaking this emanent symmetry. Yeah, without changing the emanent symmetry. So this is the way to say we turn on low energy interaction without touching the high energy cutoff. So the symmetry probably is a more precise way to make that statement. Okay. What? Yeah, certainly, I don't quite understand, but certainly for any finite L, this group is there. The representation is there, so one can do this exact analysis of representation. But it's only that when you try to see this the emanent symmetry, which try to get the Z2 part, one need to do something like this finite. You group this together as a one sector, this as another sector. And this need to be done at the L infinity limit. Yeah. So certainly, this is just a part of a story, and we can also study the low energy spectrum for odd L. Okay. This odd L have a special meaning. Is that it can be viewed as a symmetry twist of a translation symmetry, and so here the trick is that to study the anion from this anion model, not only we want to consider spectrum and their representation, we also need to consider spectrum with all kind of symmetry twist. So one symmetry twist we want to consider is a translation symmetry twist, which means to twist that we just add one side, so that we can turn one side. Then the spectrum is very different. Yeah. Actually, the Meng and Nati really studied this case very carefully. So the reason is that actually the symmetry group is changed. The lattice symmetry group is different. So now the X rotation and the X global rotation and the Z global rotation no longer commute. Okay. So you have a different lattice group. Certainly, the representation are different. And here, we still have two sectors differ by critical momentum pi. So we have two anions. But however, for the spin rotation, because they do not commute, so these representations are two-dimensional representations. So therefore, if you view this sector as an anion, so this will be the anion with a quantity dimension 2. And also there's a very slight shift, not exactly at a 0 or pi. Here is actually power 2 or 3 power 2. And so not exactly at this commensurable point. And it turns out this slight shift is a quarter times 2 pi over L. So this quarter times 2 pi over L means that this anion would have a topological spin a quarter. So they are really semions. So this is how we say, oh, there's when you compute anions, so there's also semions from this spectrum. And then now we have for the translation twist, we have two of them. And yes. No twister, yeah, that's next. Yeah. It's okay. Sorry. All the momentum here still quantized as 2 pi L times n. But however, however, the reference point, this k tilde, this k tilde actually I shift this power over 2. But the power over 2 is not an integer of 2 pi over L because L is 21. And so it's just this kind of a mismatch. Yeah, power 2 point is power 2 point is not quantized. Oh, sorry. Yeah, so it's a kind of trivial finite size effect, but somehow you can get the topological spin this way. It's kind of interesting. And then this is the case. Here we really do the Z2Z symmetry twist. And here the momentum no longer quantized as 2 pi over L. The translation in the lattice, this translation, L translation and the Z2T twist combined to this Z2L translation. It's combined translation and the spin rotation. So the crystal momentum quantization are all different. Yeah. Okay. And in this case, this Z2X rotation do not commute with this translation. So actually under this Z2X rotation, 0 and pi kind of switch. So therefore, this 0 and pi crystal momentum, they form a single representation. Actually, they form a two-dimensional representation. And so these 2 points are really same representation. So they labeled by the same. So we have a two-dimensional representation. That means we have some anion with a quantum dimension 2. Okay. Again, we have two of them. One is with crystal momentum 0. Another is here. This one have a shift. This shift actually is 2 pi over L times 1/2. This 1/2 from the symmetry twist. Yeah. And so that means so this one actually is have a topological spin 1/2. So it's a fermion. If you see from Einstein model, they are the fermion. Okay. So basically, that is the story. And so we can also do the Z2X twist or Z2Y twist. You know, you get similar pictures and collecting all those anions, and we find 22 of them. And here is now direct calculation. Then we try to think which anion model with 22 anions which fit the data we collect so far. And there's a familiar one, which is a D8 quantum double, which actually fit all the data we have so far. So we guess, yeah, maybe the multi-tensor category we want to compute is a D8 quantum double. Yes.
How you were fitting the anion model to the spectrum? I understand that you have some details.
Yeah, basically, yeah. For example, in this case, this particular anion have a quantum dimension 2, and also have a spin 0. Then this one also have a quantum dimension 2, but a spin 1/2. So basically, we collect 22 anions and their topological spin and their quantum dimension. Yeah. Many other spectrum which belong to these two classes. So these two have a different representation of the symmetry. Other spectrum are connected by the local symmetric operator. So they belong to the same class. So here we consider different symmetry representation. So they are not connected by the local symmetric operator. And so that's a different sector. Yeah, this is really from operator point of view. The two states that connect by local symmetric operator will regard as a same class, same anion, but the one which do not connect by local symmetric operator are regarded as different anion.
How do you decide how many of these guys to keep?
Yeah, I think we probably draw a line here. We consider a different representation. Actually, this is very interesting. We may have a new representation out there, and then we won't consider them. Yeah, so there is a choice of energy scale. Which representation we take depend on the energy scale. Yeah, this part is this emergence. And so here we only take these few lowest energy station. But indeed, in principle, you could find some totally different representation here. Then that would be the missing representation, not in the anion model. Yeah. That's an open question. Yeah, that's really, yeah, this is some drawback of a current calculation. We only get the topological spin and the quantum dimension. And in this calculation, the quantum dimension is always integer. Using this picture, we never get a non-integer one, and we should have a non-integer one. So there should be a better version of this approach, which you can really compute we can see the fusion rules. And then from fusion rule to compute the quantum dimension, rather than from degeneracy. Actually, from degeneracy to compute the quantum dimension is an accident in this particular case. Not generally, this correspondence should not be there. And but fusion rule, yeah, I don't know how to compute fusion rule. Yeah, this is a very, very interesting question. Yeah. Yes.
Can you say more why the topological spin related to momentum?
Yeah, in the partition function, there's a tau. The imaginary part of tau is like time evolution, and real part is a spatial translation. And this tau dependence have a certain feature, and which relate to this spatial translation, and that's crystal momentum. And also tau dependence also in conformal field theory is a conformal weight. And so the conformal weight is a topological spin. So that's how things get connected. Yeah. Yes, I think so, yeah. Because if you don't have a translation symmetry, one don't have a conformal field theory or yeah, I think, yeah, if you really don't have translation, I think there will be trouble. Yeah. Okay. So so this result is some guess is a quantum double of a D8, and for the quantum double of D8, actually there's an automorphism of this thing MTC. Which happen to form a Z4, S4 group. So you may say, what is the meaning of this anion model or this model tensor category describing symmetry? And the physical meaning is really that this XYZ chain can be viewed as a slab of a D8 gate theory, which is a quantum double of D8, means D8 gate theory. Then it have this one so-called symmetry boundary, which have a large gap, and another dynamical boundary described by anomalous quantum field theory, which describe low-energy dynamics of the XYZ chain. So this so the XYZ chain kind of is isomorphic or equivalent to this kind of slab. Okay, yeah. So then from this picture, we can find the application of the SIM MTC. Once you identify the onion model describe the symmetry, what kind of use it has. So one useful thing is that we can study the gapped phase, because the gapped phase corresponds to a gapped boundary of this SIM MTC or this SIM topological order, and also from mathematics, the gapped boundary are classified by so-called Lagrangian condensible algebra. So from the Lagrangian condensed algebra of this category, you can classify all possible gapped phase. So that's one very direct physical application. Yeah.
You did exact analyzation to see what the emanent symmetry is.
Yeah.
What is the process of? Can you extract it without solving the model? Can you extract it from the lattice model? What is the process?
Yeah, actually, exact analysis is not very. It's not used very much. The exact analysis really to allow us to look at the low energy part, basically reject certain representation which might only appear at the high energy. So that's the only thing we use in the exact analysis. Otherwise, if you don't have a analysis, we can just say that, like, for example, for this, we have a exact lattice symmetry group. It has representations, but we cannot take all the representation as onions. And so this exact analysis tell us what is the low energy sector and allow us to reject some representation and include some representation. So this selection representation is that's where the energy scale comes in. So energy scale is indeed very important. If there's other way, you can identify so-called low energy sector of a representation. That's enough. You don't. So actually, in that dimension, overkill here. Yeah, we just want to get the low energy sector reject certain representation. Yeah, and in particular, like this the 2L representation, there's a crystal mountain near this power 2 here. We reject that. However, if some other model, this power 2 become low energy, then the eminent symmetry from translation will not be Z2, but it will be Z4. And then they have a different story then. Yeah, that's the reason. So basically, then we can compute this so-called condensed algebra, which condensed algebra basically is a collection of onions which can condense together. And the Lagrangian condensed algebra basically means the maximum set of onions which can condense together. So basically, condensed algebra is a fancier or maybe more complete way to do condensation in a very consistent way. And then certainly different condensation give rise different phase. So it's very natural physically why the condensed algebra classify phase of matter. And but however, in mathematics, mathematicians gave us a way to computing this condensed algebra from modular tensor category, and we find there's 11 of them which is grouped into this 3 class connected by automorphism of this MTC. And so from this condensed algebra, we can obtain gapped phase of XYZ model, and assuming only the low energy excitation interact here. So if you assume only low energy excitation interact, there's 11 possible gapped phase. Certainly there's a dimer phase, there's an antiferromagnetic phase in XYZ direction. And interestingly that these 3 antiferromagnetic phases in XYZ direction are connected by the S3 automorphism of this MTC. So that's actually became the part of SO3 spin rotation symmetry. However, the S4 automorphism connecting these all 4 phases together. So this is a kind of well-known result. Somehow the dimer phase and the antiferromagnetic phase are connected by the emergent SO4 symmetry, and which in this story is encoded in this S4 automorphism of this onion model. And then we have this some kind of canted antiferromagnetic states, and also this kind of antiferromagnetic phase with some kind of ferromagnetic component. And these 3 XYZ direction are connected by S3 automorphism, and these three also connected by S3 automorphism, but these 6 are connected by S4 automorphism. So there's a 4 SO4 connecting these 6 phase, and and there's a predicate condensation which do not connect to anything, and which actually determine this symmetry boundary. Yeah. So essentially, to summarize that this eminent symmetry of X-ray chain is described by this D8 quantum double, and this D8 quantum double allows us to compute this 11 gapped phase, and there's also non-Lagrangian condense algebra, which give us information or maybe constraint on the gapless phase, and that's be more interesting. Yes. Yes, yeah. So yeah, this is, I also cannot say that very precisely, but naively I would say that if you have a turn interaction among those low energy stations without touching the high energy stations, so I can imagine my interaction kind of smooth, only connecting 0 and pi, but not other. So if have some way to turn on interaction only among low energy stations, and then you are allowed to make a strong interaction without affecting this UV part, then the claim that if you turn interaction in such a way, there's only 11 gapped phase you can induce. Certainly, if your interaction bring down some excitation at the pi over 2 down to low energy, then that will give you a new phase. Yeah. So there's roughly it's a kind of neighboring gapped phase of a Heisenberg chain. Yeah. Yeah.
Yeah, thank you. A couple of quick questions.
So do you know how to write the lattice Hamiltonian that has all these 11 gap phase in this chain?
Oh yeah, that's a question. We haven't done that. So basically, presumably, one can write down the perturbation to the SO3 has a model and realizing all these gap phase. Yeah. These spin patterns are obtained because those onions. We know the representation of those onions. So if you know which one condense, we probably can guess what kind of spin quantum number is induced. So that's led to this. And then from this picture, maybe one can design interactions, which is realizing this around the Heisenberg model. Yeah.
Symmetry, is it clear what terms added to the Hamiltonian will break this symmetry at low energies and which not, or it's a hard question?
Okay, let me put it this way. So far, actually, I'm only talking about the eminent symmetry. This quantum double D8 really the eminent symmetry. So therefore, they are exact at the low energy. Then if you add a lattice Hamiltonian, the lattice term which do not break this pi spin rotation, then this eminent symmetry will be exact. As long as you do not touch the high energy part, then the low energy effective theory would have this eminent symmetry, and that would be control the low energy phase. Then the claim that if you do that, there's only 11 gapped phase. Yeah.
Great, thank you, Sharon.